This papyrus is over 3,500 years old. This is the earliest known mathematical text where we know the name of the author. Someone called Ahmose, is written just down here somewhere, wrote this thousands of years ago, which makes them the first that we know of maths author. And every couple of years, I become the most recent known maths author. So I feel a certain kindred connection to Ahmose. In fact, when my book comes out in April 2024, we will once again bookend all of known authorship mathematical literature. Pre-order link in the description below if you want to get involved in that special moment. But I'm incredibly excited to finally see this incredible mathematical text. Most of it is worked problems. I don't want to call it a textbook. It's basically a textbook. And there's over 80 problems that are explained in detail and some hints for how you can work them out as well. And by my count, feel free to argue with me, there are 10 problems, which are how you divide loaves of bread between people. There are 6 problems with how you calculate the area of a field. There's another 6 problems which are like the volume of grain. There's even some problems about the angle of the slope on a pyramid, which is a bit of a cliche. Come on, Ahmose. But in terms of Egyptian writing, this is absolutely incredible mathematics. And the British Museum have very kindly got it out for me. And it means I can try and find, there are three significant bits of mathematics somewhere in this papyrus that I want to hunt down. Spoiler, the last of which is pi. I'm here with Ilona, one of the curators at the British Museum, because while I think I could probably decipher the maths, I have no idea what the hieroglyphs are saying, but you understand the hieroglyphs. Mm-hmm. Okay, so between us, we're going to find the maths problems in here. Actually, we're going to start, I think this is the beginning here?
Yes, so we have the beginning here. They would have written the papyrus from right to left, as is most usual. You may see that the individual signs do not look like the hieroglyphs you find on temple walls, on the walls of tombs, because this is a handwritten version of hieroglyphs. So because it's written with brush and ink, yep. And written on papyrus, they write a bit more smoothly, and especially in mathematical texts, they abbreviate a lot. And that's what makes the script so particular. It's a kind of abbreviation that you do not find in other ancient Egyptian documents, which makes it even more difficult to read.
So where's the name of
Yes, so
Ahmose?
We have the title of the papyrus here, which starts with something like a correct calculation.
Oh,
which
nice.
is useful to know what you're looking at. And then it says something quite cryptic about knowing all the things and all the secrets and basically everything there is in nature.
That's a classic.
Yes,
mathematicians always exaggerate how important the math is.
Yes, everything goes back to mathematics. It's a bit damaged, but it says it's written in year 33 of the king of Upper and Lower Egypt. Apophis or Apipi, Apophis, who is a king of the 15th dynasty, and he reigned more or less around 1550 BC.
Right.
And with the 15th dynasty, we are in the second intermediate period in Egypt, where the centralized administration collapsed, and the country was basically ruled by foreign rulers, the so-called Hyksos, the Hekagasu, the foreign rulers. But interestingly, he says that it was copied from an older text, made in the time, and again he refers to the king, Amenemhat III, who's a king of the 12th dynasty, so a bit more than 300 years earlier. And then here is the name of the scribe Yahmesu, or Ahmose, which is this sign. It's basically a moon sickle.
Oh, is that like the sweeping one there?
The kind of, the half round with the dot. And then mess, a mess sign, S as a phonetic complement, if you want, U. And then, because the name means something like the moons were born, there is a determinative of a woman giving birth.
Right.
To enhance the meaning of the name. And then you have the typical determinative indicating that we have a male person here. And then it says again, wrote this book, which is a little bit superfluous because it was already said before. But in case you doubt,
that's authors for you.
Yes, he wrote the
book. They really want you to know they wrote the book. So how would you pronounce their name in Egyptian?
Yahmesu.
Okay, yeah,
In this
but
case.
we say
Ahmozi.
Ahmozi.
It was a very, very common name. So
Oh.
we can't really pinpoint a name to a certain person because it was a very popular name.
something else we have in common. Number one, I want to find examples of classic Egyptian mathematics. They always did things with unit fractions. They had a fantastic method using doubling to do multiplication. So I want to see examples of both of those. So this starts with, I'm hoping these are tables of fractions being split into smaller fractions. So can you show me some numbers and I'll see if I can work out where the fractions are.
Yes, so this first part mostly has numbers and
Right.
less words, which makes it much more difficult for me. But it's basically full with everything you see are numbers. They're just here and there. For example, you have Sekem, which means something like to calculate. You have Nis, which is also a kind of calculation. And then you have the calculation. So basically it's telling you, in this case, if you want to divide 2 by an odd number and it gives you the odd number, then do this and this and this and you'll
Yep.
get the fraction. The additional difficulty is that in mathematical text, everything is even more abbreviated. So all the little dots you see is the sign for fraction.
Oh, they're the fraction symbols.
Yes, so the fraction symbol normally was a half mouth sign.
Right, yeah.
So like basically a little bit like the moon sickle we had in Yahmesu's name.
I'd always assumed it was like a loaf of bread or something.
It's
The
originally the
fraction.
mouth.
It's the mouth.
Yeah, and then cut into half.
Huh.
It becomes an abstract sign for fraction. But in mathematical texts, because they use it so often, they abbreviate it by a dot.
So the dot means fraction.
Yes, or divide into or something like this. They don't use operational signs very often, so the kind of actions you have to do are not expressed.
Right.
And on the other part of the papyrus, they are expressed in words. So we don't have these signs like plus, minus, or anything like that. So ancient Egyptian mathematics works with the decimal system. So you have 1, 10, 100, 1,000, and so on. And if they needed 400, they would just put 4 times the sign 400.
Right.
However, in these kind of very specialist mathematical texts, they do have certain signs for these numbers. For example, if you look at this one, which looks a bit like a plant or something,
Yep.
this is 2/3. So
Oh.
that is a fraction.
Is it the line down and then the little
and
tick
then the
next
little
to it?
tick,
Right,
yes.
got it.
That
There's
is
one down here.
Yes, that is 2/3. Otherwise, fractions are how do you call this in mathematics? It's always 1 over.
Yes,
Yeah,
unit
so-
fraction.
Yeah.
Yeah, because famously, Egyptian mathematics, they loved unit fractions. So I was told it's all unit fractions, but they will use 2/3, which makes
Yes,
sense.
yes.
And sometimes 3/4.
Yes, a 3/4 is a cross
Oh.
usually. And then there's some odd signs in between. For example, this little sign here is a bird. It's a gem bird. It's picking on the floor. It's the word gem is the verb to find.
Oh, okay.
And you have that regularly. So if you find this, you have to do this.
I believe, in theory, this is a list of fractions up to 101,
Yes.
2 over 101,
Yes. This is
and it shows you the smaller fractions that you can turn each one into.
So, for example, here
Yep.
you have 2,
Yep.
and then there's a Genet sign, which is something like take out
Yep.
from that. We have a sign for 10 and a sign for 7. So 17, so 2 over 17 is?
Yep. Ah, so this is breaking down 2 over 17.
Yes.
Oh, that's great. So you got to turn 2 over 17 into unit fractions. Here's what we're going to do.
And then I pretend.
Ilona's found a bunch of fractions here. We can't work out what they're all doing. So you're going to translate this with the help of the text to give me the fractions, and I'm going to try and work out the mathematics
Okay.
of what Ahmozi was trying to do with those fractions. So
Yeah,
we
but-
found the one which is 19.
Yeah, 19, but then there's another one here next to it.
Okay,
which
should we
is
do the one
again
that's next to it then?
19.
So this will be, yeah, they're trying to work out 2 divided by 19. They're doing a 12th of 19, and a 176 of 19, and 114 of 19. 1 2/3, a third, a sixth, a 12th. And what are they dividing that by? Yeah, they're doing division over here. So there's a famous method used in Egyptian mathematics where you double one number and you're keeping track of how many copies there are in the other column. Is that in here somewhere? Is that?
Yeah, so it's from right to left. So you have, so your first column would be 1 2 4. So you see 1 2 4, the dots basically.
Yep.
Next to 1 is 19. Next to 2 is 38. Next to 4 is 76. The remainder is 1/6.
So whenever we see here the dot, 2 dots, 4 dots, that's
Depends. If
Depends.
It's, yeah, it depends. So if it's with a line underneath, you're in the hundreds. But here, when they are by themselves,
Yep.
it's 1
1
2
2
4.
4.
Yeah.
That's amazing. Okay, we're going to try and find the bread one.
I mean,
Problem 40 is one where there's a sequence,
okay,
if you can find 40.
yeah, 40 is the first one after the break. Yes. So for man, and then you have the number 5,
Right.
7. So that's for man. So you have 5, and then you have a fraction of a dot over a 7.
Oh, a 7th, right?
So a 7th of 3. And then you have cheriou, which is the word, it's a preposition, it's the ones who are above. 2, man 2, those below. So I think that's part of the calculation. Yeah, so you have to divide 100 loaves among 5 men in such a way that the shares received shall be in arithmetical progression, and that 1/7 of the sum of the largest 3 shares
Right.
shall be equal to the sum of the smallest 2.
That's a great problem.
What is the difference of the shares?
That's excellent.
You have totally lost me here.
That's incredible. If you want to try and solve that problem, I will put the exact wording of that in the description of the video. See if you can solve this ancient Egyptian bread problem. Number 2, pyramid calculations, particularly bordering on trigonometric. I want to see some gradients of pyramids.
These are 6 practical problems to measure the slopes of the pyramid. So they're giving you the base and the height.
Oh, and you have to work out
You have
the
to work
slope of the...
out the
oh,
slope.
nice. It's a tangent.
Yes. So here again you have
Something 60.
360. Aha Chabet is the length.
So the base is 360.
Yes, so the length is 360,
there,
and then
yeah.
you have 250. The 2 is
the 200, yeah.
the line
and
with
then
the dot.
is that a 5?
Yeah, that's the 50. This this thing with the
Got it,
thing
with a
in the
little
middle.
tick in the middle. Yep.
And then you have, whenever you see like this kind of, like this,
Yep.
it's an abbreviated version of the owl, the M, the identification M. And then you have the per messou. Per messou is the height.
Right.
So 250 is the height.
And 360 is the base.
And then it says, give me the secant. The secant is the slope.
Yep. So what they're doing is they're basically calculating the tangent
Yeah.
of the pyramid.
We can look at it. It's 52.
Strictly
I believe,
speaking,
eh?
it's the cotangent, but I'm going to call it the tangent. So I've been calling this the Akhmosi papyrus, but it's got a different name on the box.
Yes, that is the name of the person who purchased the papyrus in the middle of the 19th century, Alexander Henry Rhind, a Scottish lawyer, who bought those 2 pieces in Thebes, present-day Luxor.
Yep.
And a few years later, it came to the British Museum. We acquired it in 1865, to be precise. And it was very common in those days for a papyrus to be named after the person who purchased
Person who
it.
paid for it.
And so that's why his name is on the frame. Later, a very small piece that was in the middle of the two pieces.
So there should be one continuous
It's one
piece.
continuous roll that consists of 14 individual papyrus sheets that are pasted together. You can see one sheet
That's
joined
a seam
here.
there, right?
Yeah, a sheet join, we say, and in total it would have been about 5 meters.
Wow.
This is a normal size.
Standard size.
We have Book of the Dead that are equally long, and an American dealer purchased a small piece of papyrus that later appeared to be part of.
Part of the in between bit.
Yes, and that made it to the Brooklyn Museum. It's quite small compared to this one, and it has the beginning actually of a few of these problems that we see here.
Ah.
And then we know that a part of it must be missing in the middle.
There's another bit
There's
that's still
yes.
never surfaced.
Yeah, but a small part. We have most of it here.
Okay. Number 3.14, it's pi. You can't do maths without pi. I really want to see how ancient Egyptians used pi and what value they were using. So this is problem 48,
So
yeah.
this calculation is using cetat, which is a measure of volume,
Right.
to measure the volume of a cylinder.
This is the volume of a cylindrical granary full of grain. Got it.
And I mean, this is one of the practical problems that was obviously very important to them because they paid people in rations, in grain quantities. They didn't have money yet. And I believe that this calculation is to measure the circumference of a circle.
Right. For the two problems that involve circles where they're calculating the area, the technique is to subtract 1/9 of the total of the diameter and then square the result, which is nice and clean. That's a really crisp way to get the area. But what is the implied value of pi? Well, if we convert that into like our modern algebraic way of understanding things, we're taking 8/9 of the diameter, but the diameter is twice the radius. So actually we're doubling the radius, then multiplying it by 8/9, and then squaring the whole thing, which means the implied value of pi is 4 times the 2 squared times the square of 8/9. If you work out 4 times the square of 8/9, it's 3.16, which, I mean, might sound bad, but that's within a percent. That's only about 0.6% off the true value of pi. And so thousands of years ago, they'd worked out that value of pi was good enough to do the calculations for areas of fields and volumes of grain in cylindrical granaries. I mean, that's amazing. What an incredible value of pi.
1/9 of... so 1/9 of 9.
Yep, because that's the diameter over here we have.
Yeah, and then the m is like an identifier, namely 1, and the remainder is 8.
Okay, yep.
That makes sense. I understand that.
Yeah, there you go.
So it's 64. So this is very abbreviated. So the thing with the 3 strokes
Yep,
is 60,
that's 60.
And the horizontal...
And that's a 4.
Yeah, so that is an abbreviation of 4 dots.
Is that why there's a line here for 4 dots?
Yeah.
In that doubling sequence?
Yeah,
Okay,
this
that
is
makes
again
sense.
1, 2, 4.
Yep.
Yeah. 64,
64.
that's the same.
Yep.
You recognize this was the same as 64.
Yep, same 64. Yep.
Um,
Half or something.
R tap. So R tap is something like up to times.
Oh,
R
okay.
tap 10. This is the 10.
Yeah, the 10's the height. Yep.
And that becomes Japer. So this is Japer RF. This scribbly thing you see here is a beetle.
Oh.
And the beetle is the verb to become, which you find often in the papyrus because this is kind of saying it becomes.
So the bird is to find,
Yeah.
and the beetle is to become.
To become. Yeah. So it becomes M again for the identifier 640.
Yep.
That is the 100.
That's hundreds.
And
yep.
the 3 dots above it is 4. So the 100 with 1 dot is 200, with 2 dots is 300, with 4 dots, with 3 dots is 400.
Yep.
And then it's the abbreviated version for 40.
So that is Ahmosi's incredible mathematical textbook. And I love the title, like Correct Calculations And I don't think they're overpromising when they say, which reveal all secrets. I mean, that's classic maths author titling their book. I think a lot of my book proposals had that exact sentence in them. And I'm just astounded how similar this is, other than, aesthetically, to a modern maths book. They were using weird abbreviations. They were giving worked examples. It's so amazing to see that, I know humans haven't changed for millennia, but it's just amazing to see across thousands of years, we've always been doing maths the same way. And you can see how deeply practical it is. They needed to know how to share bread, how to calculate the amount of grain in a granary. They had to be able to work out the area of a field. I mean, the Nile was always flooding and they had to recalculate and remeasure fields. And so I find it, almost emotional to see this incredible moment in the history of mathematics when some really advanced mathematics had been worked out, and it had been worked out for practical reasons, but you can already see the beginnings of just abstract, fun, recreational mathematics. And you can't tell me some of these problems weren't put in here just because they were fun to work out. Huge thanks to the British Museum for letting me come and have a look at this incredible document, which is not normally on display, and they don't get this out very often, so I'm incredibly privileged to be able to show this to everyone watching the videos. They have got their own YouTube channel, so if you want to learn more hieroglyphs, learn some more Egyptian script, then I'll link to some videos below, and I'm filming another video here while I'm around, which will be on their channel, and they've been very secretive about what they're going to show me. I really hope it's Sumerian mathematics, but we'll find out. Link below.